Okay, so what we're going to do is put all this together into a model that we can actually visualize. And first of all, let me talk about this a little bit. So the model that we're going to talk about is not actually the model that uh, today's quantum physicists use. We're not going to use the modern model, and you'll see it here. Is the modern model? It's called the modern quantum model. So Bohr developed the model between 1911 and 1915, and it works, but it's not very good quantitatively. What that means is it doesn't work mathematically, and that's always a problem. Physicists always like to have things done mathematically. So over the next few years, from about 1915 to 1930, really smart guys, and you probably heard of them, like Einstein, came together and they came up with the magic mathematical formula. And actually, it was this guy named Erwin Schrödinger, and here's his magical formula. Now I say memorize it, but forget it. We're not going to use this. It's a crazy formula. There's a lot of stuff here. It just looks like a bunch of Greek. And so anyways, so what we're going to do is use a qualitative model, more or less, where we're just be able to understand it by looking at patterns. So the model is, we use it for the class. And what we want to do is that now we know you can put so many electrons, energy level 1, 2, two of them. Energy level 2, you can put 8. You know that they're split up between the s and p orbitals, subshells. Energy level 3, you can put 18 electrons. You can split them up into sp and ds and so forth. But what we want to do really now is that if I have an atom like calcium, I want to know where we think where all the electrons are going to be in the atom. We know where they can be, but we want to know specifically where they are. Okay, so some of the things we're going to keep in mind is electrons will always move towards protons, and that means they will always seek the lowest energy level. Now, if there is an energy level, if one of the lower energy levels get filled up, what happens is that the electron has to go up to the next energy level. Okay. Energy levels can only accept a certain number of electrons. Okay. So energy level can take 2 electrons, and another 2 can take 8, so forth. Also, electrons, if they're given a choice to go to different subshells between S, P, Ds, and F, they'll choose S's over P's, P's over D's, D's over F. So what we have so far is if you put electron in, what it's going to do is look for a 1s. Okay. If it can't find a 1s, it will jump up to energy level 2 and look for a 2s. And if it can't find a 2s open, it will go to 2p. If it can't find it, and so forth. And we're going to see how that works out. And so if a subshell gets filled up, an S, what it'll do is move to a P. A P fills up, move to a D, so forth. So what we're going to do is we're not going to be drawing circles. It'll get really messy if we do that. What we're going to do is we're going to draw kind of like an upside down staircase to represent our model. And we're going to call that model the orbital energy diagram. And here you go. Okay, so the way it goes is this. We know that energy level 1 can have a S subshell. And the S subshell has one S orbital. Orbital is going to be represented as squares. Energy level 2, we said, has 2 subshells, an S subshell and a P subshell. And the P subshell can have 3 orbitals. Energy level 3 can have an S subshell with 1 S orbital, a P subshell with 3 P orbitals, and a D subshell with D orbitals, 5 of them. And if we want, we can keep on building. This at energy level 4 would have one S, would have an S subshell with one S orbital, have a P subshell with 3, have a D subshell with 5, and then would have an F with 7. So this is going to be our model that we're going to drop our electrons in. Okay, so the electrons can only fit into these squares, and you can only put 2 electrons in each square. The electrons are always going to move towards the bottom, energy level 1, and fill up, move up, fill up. Okay, so we're going to just get to it, and placement of electrons of an atom into this model. We're going to start out with lithium, and as I said, this model is called the orbital energy diagram, OED. So lithium has 3 electrons. We know that because it has 3 protons, and we're going to say that right now that the number of electrons equals the number of protons. It doesn't have to be that way, just like we've learned about ions. For instance, like sodium has a plus charge when it's an ionic compound. That means it's lost electrons. But we're not going to deal with that. We're going to just deal with atoms that have neutral charge. So lithium has 3 protons, and we're going to say it has 3 electrons. So how do they fit into this diagram? Okay, so there's 3 electrons. So the first electron is going to come in, and it's going to go as far down as it can. It's going to go energy level 1, and it's going to go in as an up arrow. And anytime an electron goes into a box, it's always going to go up. And that's just convention. So we got 1 electron. So it's got 2 more. So the second one comes in. Well, there's enough space in each square to put 2 electrons. So the second one's going to come in, but it's got to have an upside down arrow. Okay. Now this box is all filled up. So energy level 1 is all filled up. It has 2 electrons. All right. Now there's actually a kind of a big deal here, is if you put the arrow pointing up, you're breaking a basic law in science called Pauli's exclusion principle. But we won't be getting into that. All right, so that we have now it has another electron. So the next electron comes in, and it sees that it can't go into the first energy level because it's all filled up. So it has to go to energy level 2. And it has a choice picking any one of these 4 squares or these 2 subshells. It has a choice between S subshell and P subshell. And remember, electrons always pick S over P, so it's going to end up here. So what we have here, this is the orbital energy diagram for lithium. It has 2 electrons in the first energy level and 1 in the second energy level. And this is the actual how we think the electrons are situated in the atom. So lithium has 2 energy levels. The outer energy level has 1 electron. And this is called the valence shell. The energy level, and it's energy level 2. And the number of valence electrons in the valence shell is 1. Okay, so the outer energy level atom is called the valence shell. The number of electrons in the valence shell are called the valence electrons. And these are really the most important electrons of an atom because they determine the chemical activity. And so we're going to be really focusing on knowing the valence electrons and the valence shell. And also, as we just said, this model is called the orbital energy diagram, or OED. All right, now let's look at an atom that has 4 electrons, beryllium. Okay, so again, it has 4. So the first one goes up, the second one comes down, 2. Third one goes up just like lithium, and the fourth one, well, there's space still in this guy here, so it goes right here. So for beryllium, it has 2 energy levels. The second level is a valence shell, and it has 2 valence electrons. Okay, boron has 5 electrons. Do the same thing. First electron goes in, up, second one down, third one up, fourth one down. So now you filled up the S and energy level 2. Now you have to go to the P subshell. And so you put the first one in here. Actually, you could put it in any one of these 3 squares because they're all actually equivalent. But we usually start from over here. So this is the orbital energy diagram of boron. It has a valence shell of 2, and it has 3 valence electrons. 1, 2, 3. All right, let's do carbon. So carbon has 6. So you go 1, 2, 3, 4, 5, just like boron. Now, here's the thing about now we have the 6 electron. Now, you may think that it might pair up in the same square as the one that we put in already, okay? Just like in the 2s and the 1s, but it doesn't, okay? That's because that electron can go to any one of these 3 orbitals, okay? And would rather go to an empty orbital in its same subshell than the pair. So what you're going to do is that the first one comes up, the second one will go here, up, and the third one will go up. And then you'll come back and do the downs. So you do the ups first and then the downs. So this is wrong. So it's going to be up, down, up, up. Okay, so carbon has valence shell energy level 2 and has 4 valence electrons. 1, 2, 3, 4. Okay, nitrogen, again, so it has 1, 2, 3, 4, then up, up, up. All these guys are the same. They're not, these guys are together. Okay, so up, up, up. They're a set called a subshell. So nitrogen has energy level 2 with 5 valence electrons. Oxygen has 8 electrons. 1, 2, up, down, up, up, up. And then you can start going to down. So oxygen has 2 energy levels. A valence electron, a valence shell 2, and has 1, 2, 3, 4, 5, 6 valence electrons. Okay, I'm not really sure I left off here. I had a phone call to answer. And basically, oxygen has 6 valence electrons. So they go up, down, then up, and then down. Then fluorine, same thing. It has 9 electrons, do the same pattern. Up, down, up, then down, and has 7 valence electrons, and valence shell is 2. And neon, to finish it off, is as you see here. Okay. And then you have sodium. Okay, so sodium. So it's has 11. So it's up, down, then up, down. Now you're done with the P subshell and the S subshell and the whole energy level 2. So the next electron has to go into energy level 3 and the S, and it goes as an up. So sodium has energy level 3 as its valence shell and 1 valence electron. Okay, magnesium has 12 electrons. We do the same story, up, down, and so forth. And the last one comes right next to it. Okay, so now you have a filled up S subshell. Now the next atom would be aluminum, and then again, just like for boron, you go, it would come in and go up here, and then the atom with 14 electrons, silicon, would have its electron go here, and then phosphorus would have electron go here in the third orbital of the p subshell, and then sulfur would come here and go right next to the first orbital. So one thing I'm going to ask you to be able to do is draw the orbital energy diagram for any atom 1 through 18, or through hydrogen through argon, and we'll have a worksheet for that. Okay, so far, if we're gonna we'll take a look at the periodic table as well when we do this. So hydrogen, well, let's go start with lithium. That's the first one we start out with. So lithium had 3 electrons. It was in it had electrons in the first and second energy levels. So the valence shell is the second energy level, and it had 1 valence shell. Beryllium had 4 electrons, 2 valence. Second level was the valence shell, and it had 2 valence electrons, 2 in the first shell, 2 in the second shell, and so forth. And so this is what we just did a few minutes ago. Okay, we determined all this stuff. Right. Now, if we go and look at the periodic table, what you'll notice is that okay, right, is that you have okay, that lithium is found in the second row, and all of these guys are found in the second row, and they all have, so they have 1, 2, 3, 4, 5, 6, 7, 8. Okay, then we started up sodium, and sodium is found in the third row. It had 3 valence shells. I mean, it had a valence shell of 3, but if you notice, if you compare sodium with lithium, they both have just 1 valence electron. Okay, so if you go back and look at it, what we just did, lithium had 1 electron in its valence shell, and sodium also had 1 electron in the valence shell. And you notice where they are. They're both in the first column. The difference is what row they're in. So again, and if we looked at beryllium, we saw that beryllium had 2 valence shells, 2 energy levels, had 2 valence electrons. Okay. It's in the second row in the periodic table. Then we just did magnesium, and magnesium has 3 energy levels, its valence shell, and it has 2 valence electrons. Notice it has the exact same number of valence electrons as beryllium. The difference is what row it's in, okay, as far as the periodic table goes. So if we go down all the way across, what we'll see is that all these elements, carbon, nitrogen, oxygen, they have sort of they're paired up with other atoms that have the exact number of valence electrons. So silicon has 4 valence electrons, and so does carbon. Okay. In fact, every element in a column, okay, and we're going to see this. So all the elements in column 1 have 1 valence electron. All the elements in column 2 would have 2 valence electrons. All right, and we're going to see that. We're going to see how this works in a little bit. There is some things we're going to have to be more explicit about, but there is a relationship. This is that the number of valence electrons doesn't seem to vary as you go. As you look at the periodic table, it's always going to be 1 through 8, 1 through 8. Okay, so let's go to potassium. So potassium has 19 electrons. So let's drop them in. So you go 1, up, down, then up, up, down, down, down. Okay, now there's a total of 10 electrons. 11th one goes here, 12th here, then 13, 14, 15, up, 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 then down, 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 and then the 19th, you'd think it would go here, because we said is that if a subshell gets filled up, what you do is you go to the next subshell. Well, that's not the case. Okay, it does go to the next, goes to another subshell. It can't go, you can't put any more electrons here, but it doesn't go to the subshell. Instead, it does something weird. It goes up to the floor S. Okay. All right. And the reason it does that is beyond me talking about it. It's too complicated. In fact, I don't even know if anybody I've read things I've read, they haven't been a real good job explaining it. Okay. So the 9th one goes here, and it turns out the 20th one would go here for calcium, and then the 21st doesn't go here, it ends up going back down here. Okay, so what we end up doing is we end up getting a big mess once we get past an atom with 18 electrons. This model, the orbital energy diagram, really gets a little messy, and we'd rather not use it. And so what we're going to do is we're going to move on to another model that's going to help us figure out where the electrons are in the atom, but not using the orbital energy diagram. Okay, so here's what I just said. And like I said, so what I really want you to do is know how to do the orbital energy diagram for the first 18. And what you need to do is tell me how many valence electrons are in the valence shell. And that'll probably be worksheet number 1. Okay. All right.